All right, here we go. So, like I mentioned last class, today we're going to look at the different isentropic efficiencies of the different components, like the turbine, the compressor, the nozzle, and probably a valve or a pump. Okay, so let's look at isentropic. So 91, isentropic efficiency of a turbine. Okay, so isentropic basically means that the change in entropy is zero. So we go back, what is the physical meaning of the entropy? Is how well you are using the energy, no? So if the entropy is zero, that means that you're not wasting any energy. So let's say this will be the ideal case on about how to use the energy. We saw that if you waste some energy, then the entropy is different than zero. Okay? So what would be the isentropic efficiency? So the efficiency should be equal to what? Whatever would be the actual performance of your component divided by what? By the ideal performance, no? Like if you do not have any loss of energy. And this is the isentropic performance. Okay, and in our case, the efficiency will always be between, I'm going to put 0, but obviously it's never going to be 0 and 1, okay? All right, so the first component we're going to study is a turbine. So remember the figure for the turbine. So this is our turbine. This is our control volume, and many times we have, like, let's say, a flow coming in this way and leaving this way. It doesn't matter how you do the way they come in. But basically, the turbine is what is at the back of an engine, no? And is what transforms all the entropy into new speed, no? It's the one that creates power. All right, so if we do the enthalpy entropy, so again, the turbine is the one who's going to transform all the enthalpy into power, no? Okay. All right, so this curve is not that important, but let's just say to show you that it can be at different states. And let's say we're going to deal with 2 lines of pressure. So this will be, oops, no, I want to ask you that question now. So let's see on the turbine, which pressure should be higher, P1 or P2?
P2.
So P1 or P2?
P1.
P1, because remember, if it was an aircraft, here you have the compressor, which compresses everything, no? So what is the enthalpy? Enthalpy is internal energy plus work done by the pressure. So in here you increase the pressure by having a compressor, and then you increase the internal energy by just burning fuel inside, no? Now the role of the turbine is to transform all that enthalpy here into kinetic energy, no? Yeah, okay. So P1 is higher, so P1 should be the one on top. and this one should be P2. Okay. So if we look at isentropic, this should be a straight line. Mine is not that straight. We go here from 1 to this called this one, 2s.
Hey, Professor, we can't see your screen.
Oh, did I not share the screen? Okay, why not? We can't see anything, Professor. We can see the screen. Okay, let me pause. All right, guys, sorry for a little technical issue, but okay, so basically I was saying that the efficiency for anything is what? The actual performance divided by the ideal performance, no? Okay, so in this case, if we look at the turbine, the pressure going in should be higher than the pressure going out. And if it's isentropic, this should be a straight line. Now, if this is not an ideal turbine, what's going to happen to the entropy? It's not going to be 0, and the entropy needs to be positive, no? Should increase. So what does that mean? Is that we're not going to be here anymore, what this should mean delta S equal to 0. Our tool should be somewhere over here. Okay, with increasing entropy. All right, so now maybe I can do it here. So what would be, so that distance over here should be what? H1 minus H2S and this one here will be H1 minus H2, okay, in function of the enthalpies. So what will be the efficiency? We call it with the letter eta. So we just say it would be the actual divided by the isentropic So this will mean what? This will be the actual work or power to the isentropic Okay, so if you remember, if this is this an open system or closed system? This is an open system, no? Or control volume. So in this case, everything is in function of what? Of the internal energy or the enthalpy? It's in function of the enthalpy, no? Okay, so anyway, what would be the actual? So the actual work or power should be, the actual should be proportional to what? To the change in enthalpy between 1 and 2, no? So it should be like H1 minus H2 divided by what? The isentropic will be H1 minus H2S. Yeah, H2S. Maybe let me do here something very quick. Maybe I'm assuming that you remember this more than that you do. If you do the first law for this system, what would that be? Would be Q minus power plus M dot H1 would be equal to M dot H2, no? Yeah. If there is no loss of heat transfer, this is 0. So you see that the power should be equal to what? M dot H1 minus H2, no? That will be the power, okay? And you see the M's will cancel out. Okay, so let's do an example, and then we move to the, I guess, the efficiency, which is similar to a nozzle. All right, so let's do one example. You go to the next page. So it's to learn how to use the tables now with the VAT tool. So 92, example. So we're gonna have a steam turbine. Operating at steady state. Okay, we're gonna neglect any heat transfer, loss or gain, and we are going to neglect any change in kinetic or potential energy. So basically, we're gonna have a turbine here, steam turbine. Where we know that the inlet pressure is 5 bars. The temperature is 300 degrees Celsius. And that P2 is 1 bar. Okay, if the efficiency of the turbine is 0.75, what we need to find is what is the actual power produced by the turbine. Okay, so obviously this is just a direct application to what we just did. So not going to be anything different. So let's do the figure very quick. H and S. But maybe before, let's go check something before. So we know it's steam. So what is the substance? Water, no? Okay. So initially, what is the pressure? 5. So I have no idea. Do you know what is the boiling temperature of water for 5 bars? I have no idea, but we know that the temperature at 1 bar, which is basically 1 atmosphere, what should be the temperature? It's 100, no? Okay. But do you know what is the temperature of boiling water? What is the temperature at which water will start boiling at 5 bars? Okay, that's the idea behind the pressure cookers, no? It should increase, right? But I have no idea what it is. So I want to know what is the state at this point, okay? So in order to do that, we need to go to the tables. I like this one, I don't know why, but it should be identical to the other ones. All right, so let's go here, SI units. So it should be table A2. This is the temperature. We can look here either at the pressure. So what is the temperature? 320? I mean, let's look at table A3, would be easier. We have 5 bars. Okay, what should be the boiling temperature? 151.9, no? So what do we know? That it will be vapor, no? everything will be vector. Okay, so now we can go back here and at least we can do the figure, and basically it will be exactly the same figure that we had before. Let's just do it that way. So we know P1 is 5 and P2 is 1. So this is the isentropic efficiency. So if this was isentropic, what does that mean? I mean, yeah, hopefully it's that way, the figure. This should be 2s. And then what will happen if we have the 2 over here? This will be the actual, so it will be isentropic. This will be the actual. Okay. So here is S1 equal S2S. And this will be here S2. Okay, so by definition, we know that the efficiency is what? Is the actual power divided by the isentropic that we just saw was equal to, okay, we can do that later. So from here, what do we know? That the actual power of the turbine should be the efficiency times the isentropic. That's not complicated to understand. Okay, so the one of the actual. Okay, I'm using this equation here, okay, all the time. So this is actual, isentropic should be equal to what? H1 minus H2S. Should be efficiency time H1 minus H2S. Okay, so by now should be used to it. How do we find H1? We're going to use the tables, no? Okay, so in order to find H1, what do we know? What would be the state of 1? We know is vapor, no? So we know it should go what? To table A4. And we need to know two things. Like always, do we know two things? We know the pressure and we know the temperature, no? So we can find H1 from the table. So it will be here H4, P equal to 5. We are log is here and T equals 320. We look at H, we have 3005.6. 3105.6 kilojoules per kilogram. Okay, next we need to find H2S. Page 93. Now we need to find H2S. What do we know at point 2? We need to know two things. So we know the pressure, no? So we know P2 will be equal to 1. And what else do we know? Everything's on the figure. What else do we know from the figure? It's on the figure. What do we know? S2S equal to S1, no? Yeah, so S2S equal to S1, which we forgot to calculate. But from where can we find this S1? We can probably find it from the table that we were before, no? So it should be this value over here, 7.5308. You can say here 7.5308, and this was again from table A4. Okay, if you want, you could have wrote it over here. Okay, I'm going to put it on both places, and S1 is equal to 7.5308. So the bad thing about that is that we're probably going to have to interpolate. So what would be the state of 2S? We don't know, but we can find out now, no? But so let's look at it. So let's go to the tables. We know P equal to 1. P equal to 1, what is the minimum entropy that you have at 1? 7.35, no? So what is the state? It's still vapor. Correct? Yeah? Or otherwise, you could have found that from the table A3 at 1 over here. Why this is not going out? Okay. At 1 over here, what is the S sub G? Which is this value here. S sub G is 7.3594, no? The value we have for S is 7.53. That means that we are past the saturated gas line, okay? So we know we need to go to table A4 at 1, which is this one over here. Now we need to find 7.5308. So it's going to be between these two values, no? Okay, I'm going to have to interpolate. All right, so let's say we're going to be at, so as my S sub A will be the 7.4668. And at that point, I know that H, so H sub A will be equal to what? 2,716.6. So it's this column over here. All right? H is this column over here. And at 7 point, so S sub B, 7.6597. My H low will be is 2,796.2. So this is table A4 at P equal 1 bar, okay? So just as a refresher, but I should not be doing this anymore. You should know how to interpolate. What do you put on the Y? What are we trying to find over here? We're trying to find H2S, no? So you put on the Y direction what we're trying to find. And what do we know? The entropy, no? Okay, so it will be a linear interpolation. So let's say this will be point A, point B. I'm going to try to find here H2S, knowing S2S, okay? And this is S sub A, S sub B, H sub A, H sub B. So again, you should know how to do this. So what should be H2S, which would be this value here, should be H sub A plus the slope would be H sub B minus H sub A divided by S sub B minus S sub A times this increment over here would be S to S minus S sub A. Okay, so you have here all the values, S sub A, S sub B, H sub A, H sub B, S to S is the 7.5308. And I give you the value here because I have them. Today I printed, now that I pick up random stuff. This gives you 2,743.01. Okay, so finally, recalling the equation, we had that the actual work should be equal to the performance times H1 minus H2S. So this is equal to 0.75 times H1 we found to be equal to 3,105.6 minus 2,743.01. We get that the actual performance of this turbine is 2,071.9 kilojoules. Sorry for that. Okay, so you see, this is the extra work that you're gonna have to do, no, with the present problems. All right. So that's the efficiency for the turbine. Now let's look at what would be the efficiency of a compressor. Okay, I could do the one of the nozzle, but let's just do this one. So now we're going to look at isentropic efficiency of a compressor and the same thing as a pump. So basically, why are they going to have the same expression for the efficiency? All right, and I think it's just you that both have the same function, no? What is the function of the compressor? To compress the air, no? In order to compress the air, you need to use energy, correct? What is the function of the pump? If you want the water, you are a firefighter, you want the water to go to the second floor of the building, what you need to do? You need to increase the pressure, no? Yeah? So they both do the same thing. And in order to do that, you need to use energy, correct? Okay, so it would be, the expression should be similar. So I just do that at the same time. So again, the figure for the compressor but it doesn't matter if you don't do the correct one, okay? Compressor 1, 2. And since we did that before, we know this one now. The compressor is going to require work. It's not going to provide work. And this one now is easy. Compressor or pump is going to do the same thing. What should be which pressure should be higher? P2 should be higher than P1, no? Okay. And if you have a pump, let me just do a figure here for the pump. It will be exactly the same one. 1, 2. Oops, okay, doesn't matter. If you want, the pump will increase the pressure, no? So P1 should be lower than P2. Okay, same function. And this one, this will be the control volume. And in order for that to happen, you also need to provide work or power. Okay, so let's do the figure. Same thing. We do the same figure as before. HS. Now we still have those two curves. So now be careful. It's different than before. Before, what did we have? P1 was higher than P2, no? In this case, what do you have? P2 is going to be the one on top, and P1 is going to be the one at the bottom. So that means that now instead of going up to down, we go down, up. So let's say we are here at 1. And the process is isentropic. Here, this should be 2s, no? This should be isentropic. Now, obviously, if something is not perfect, what happens? The entropy increases. So the 2 will be over here. So now, be careful because it's reversed than before. So now, the change of enthalpy here should be equal to what? H2S minus H2, no? The H2S is larger. Sorry, this should be, H2S minus H2. Sorry, no, no, it's correct. This should be, sorry, H2S minus, no, this is correct, H2. And this one over here would be H2 minus H1. So this one is of no interest really. Sorry for that. And this one here will be H2S minus H1, no? Yes?
Why is 2 coming from the 2s instead of from the 1 as well?
Oh, because I did it wrong.
Yeah.
Sorry, absolutely right. Sorry, I was looking at the figure. So let me pause the recording. So sorry for the wrong figure. I don't know what happened to me. So again, this is the figure, and now we need to look at the change of entropy between this point here and this point. So this one will be H2 minus H1. And this one here, that should be a straight line. It doesn't look straight at all. This should be a straight line. Sorry for that. Will be H2S minus H1. So the efficiency, we say that will be, so the efficiency, we're going to call this one mu sub c for compressor. The one we could have called it, eta sub t, this one eta sub c will be the actual divided by the ideal. So be careful here because you're going to see what's going to happen, okay? So what happens over here? The actual here should be equal to what? H2 minus H sub 1, correct? Divided by what? The ideal, that will be H2S minus H1. This is kind of what we did before, no? Okay, but now pay attention because, I mean, you see I'm doing it following, but which one is bigger? Which one is bigger, H2 minus H1 or H2S minus H1? H2 minus H1, no? So if that is the case, the efficiency is always going to be higher than 1. Does that make sense? No, okay? So because of this, all right, the efficiency of compressor slash pump is really defined as what? The efficiency of the compressor slash pump. Since we know that the efficiency is always between 0 and 1, will just be the reverse will be the ideal divided by the actual, which this time will give you H2S minus H1 divided by H2 minus H1. Sorry for that. Okay, so be careful with that because you see, I tried to use the normal definition that we had before, and in this case, it would not work because we need to have the efficiencies always between 0 and 1. So you need to reverse the order, which basically makes sense, no? When you have to generate power, is how much power you can generate divided by the maximum power you could generate. Now, if you have something that is required to take power, now what should be the efficiency? How much power do you need if you are ideal? Okay, and how much power do you need if you're not ideal, no? So which one will require more power? The one that you're not ideal. Okay. All right, and again, let's do an example. All right, page 95. So this is trash. Okay. All right, so example. We're gonna have a compressor. Again, it doesn't matter if you don't do, you can just do a rectangle. The symbol does not matter at all. Because I have 1 and 2. This will be your control volume. And we know this is gonna require power. And in this case, they tell us that the substance is refrigerant 22, so R22. You know that P1 is 3.5 bars and T1 is negative 5 degrees Celsius. Now you know that P2, so it should be higher than P1, is 14 bars, and that T2 is 75 degrees Celsius. Okay, so we need to find what is the efficiency of the compressor. Okay, so very quick, let's just redo exactly the same two figures that we did. Hopefully I won't do the mistake anymore. So we have this one. So HS. And maybe before, let me remind the equation for the efficiency of the compressor will be H2S minus H1 divided by H2 minus H1, okay? Just copy from the previous page. So before doing the figure here, let's go and check the state, okay, of the R22. So we go here. I have no idea which one is the page for R22. So there we go, R22. So let's see. What are the two pressures we have? 3.5. What is the saturation temperature? Minus 10. What do we have over here? Minus 5. Okay, let's look at the other one and let's see what would that mean. And then at 14 is 36 and we have 75. Okay, so in both of them, minus 5, you agree is higher than minus 10, no? Yeah, and this one is easy. 75 is higher than 36. So what should be the state? They should be saturated vapor, no? They should be on the right side of the curve, okay? All right, so again, similar figure that the one we did, really. What we're gonna have here, P1, P2, hopefully I'm not going to do the arrow this time. I'm going to try to have a better straight line. This one is a lot better. So it should be 1, 2s, 2 should be here. Okay. So we can leave it that way. Okay, I'm not going to start putting everything. So basically, we need to find H1, H2, and H2s, no? So let's first find H1. We just said that we know the state is saturated vapor. So that means that we need to go to which tables? So we find out here. This is table A8. So I guess we're gonna have to go to table A9, which is superheated refrigerant, no? And table A9, table A9, and we need to know two things. At 1, we know P1 equal to 3.5, and we know T1 equal to -5 degrees Celsius. So we know two things. Remember, when you go to the tables, you always need to know two things. So from the table, we're going to find H1, but we're also going to need S1 as before. So we go to that table, we get that. So let's see, 3.5. 3.5, we look for H at -5 is 249.75. And S1 is 0.9572. Okay, before finding H2S, let's find H2. Do we know two things at H2? Yes, no? And the state will be the same one, so probably will be the same table, table A9. We need to know two things, so we know P2 equal to 14 and T2 equal to 75. So in this case, we only need one of them, H2. So we go to 14. Hopefully they have 14. Not willing to interpolate. Awesome, they have 14. I cannot remove that little figure here. I don't know why. And the temperature is, okay, 75, but it's pretty easy to do an interpolation, no? Oops. 14. So you just take the two values and you divide by 2. So if you take, can somebody do 290.01 plus 298.34 divided by 2? So you add them and divide by 2. So it will be 294 point what? 175. Thank you. So 294.175. And now we need the one that is so we need to find out H2S, which probably we're gonna have to interpolate, no? So let me go to the next page. So we need to find H2S. So again, the state will still be superheated vapor, no? We need to know two things at this point. Do we know two things? We know the pressure, no? What is the pressure? So this will be still table A9. we need to know two things. So one is the pressure, which is 14. What else do we know? No, we don't know the temperature. We know that S2S should be equal to S1, no? Yeah, over here. S1 equal to S2S. Correct? So that's what we solve here for S1. Remember? So for S1 here. So S2S equal to S1 equal to 0.9572. So we need to go to table A9 and probably to do what? Interpolate. So we have 14. We go here to 14. Where is 14? It's right here. I don't know how to get rid of that stuff. Ooh, not good. Okay. Yeah, I tried, but I cannot. Doesn't do anything.
It's probably like a sweet spot.
I don't like it at all. Let's see if it. So let's see if now it disappears. So A9, I was lucky here. 14. So here, okay. So we know this is 14 bars and the S is 0.9572. So it's going to be between these two values, no? Okay. So let's do as before. Let me write over here S sub A would be 0.9452. S sub B will be 0.9703. H sub A 281.53. H sub B 290.01. Okay, and hopefully by now you know how to do that without the figure. Okay, I'm not gonna redo it all the time. Let's do very quick here. A, B, okay. I will try to find the value here. S to S. This would be H to S. So if we interpolate, what do you get? H to S would be equal to what? HA plus the slope would be H sub B minus H sub A divided by S sub B minus S sub A times S to S minus S sub A. And to save some time, this time I have the value, so let me just give it to you. You get 285.58. Okay, so finally, recalling the expression for the efficiency of the compressor, that was H to S minus H1 divided by H2 minus H1 will give us what? 285.58 minus H1, we found that to be 249.75. H2, we found that to be 294.175. So minus H1 will be again 249.75. And this will give you a value of 0.806, which if you want is approximately 81% efficient. Okay. And now the last component we're going to do is a nozzle. So this was page 96. Okay, so now we're going to look at the isentropic efficiency of a nozzle. So there's different ways to represent this. Your textbook will use this one. One, two. So if you want, this will be your control volume. So it's the same mass flow that goes in. So let's say that here you have P1, T1, and V1. V here is not the volume, obviously it's the velocity, no? Otherwise I will do this is velocity. Here, this V here is velocity. It's not volume. So let's say in the case that V2 is higher than V1. I mean, just think about conservation of energy. If something goes up, what should happen to the other quantities? They should go down to compensate, no? Okay. So probably what's going to happen here, the pressure is going to drop, the same thing that happened in the turbine, no? Okay. And same thing with the temperature. Okay, so what is the function of a nozzle? Nozzle is nothing mechanical. If air goes over here and this cross section is smaller, what's going to happen? If you keep, so it's going to speed up, no? So the efficiency of a nozzle should be then in function maybe of the velocities. Does that make sense? Okay. What is the quantity that is related to the velocities? Is really the kinetic energy. Okay. So let's say here, let's define the efficiency of the nozzle as being equal to the change, or being equal to the actual kinetic energy divided by the isentropic kinetic energy. So mathematically speaking, this will be 1/2 m dot v2 square divided by 1/2 m dot v2s square, which at the end would just be v2 square divided by v2s square. Okay, let's just do the figure and we'll stop over here. We'll do the example next time. So we have to do a figure in this case, kind of similar as before. We know P1 should be higher, P2, we go isentropic, 1 to S, so S1 equal to S2S, and when it's not ideal, you go to 2. So the only thing here is that this time, instead of talking about enthalpies, we're going to talk about kinetic energy. So this change over here is proportional to what? V2 square over 2, the 1/2, the velocity. And this one here should be the V2s square over 2. That figure is not that important in this case. Okay, so for today, we're going to stop over here.